So quite often in statistics we try and estimate parameters. X bar, your sample mean, is an estimate for mu, your population mean. But you know that if you take a different survey, you're going to get different results. You're probably going to get a different estimate for this population parameter. So after we get our point estimate, what we do is we surround it by a confidence interval. Even though we know that this is probably not exactly what the mean is, we're hoping that we're pretty close. So we're hoping that that mu is somewhere between x bar plus e and x bar minus e. Somewhere here we hope that our true population mean is. Now, in this section, we've got a different parameter we're estimating, and the value for e really also depends on an assumption, what's going on here. And the most typical assumption for us in this section is going to be this. E is going to be t sub alpha over 2 times s over the square root of n. And that means, or this assumes, we don't know what sigma is. This assumes that sigma is unknown. And if sigma is unknown, then you have to use s. Now this letter here, even though it may not look like it, is the letter T, and it's from the T distribution. So that's a new distribution we're going to have to learn. We're going to have to learn how to calculate with it, learn where it is, use it, etc. So the T distribution came about by research by a guy who worked at the Guinness Brewery. His name was William Gossett Jr. And he was doing investigations involving normally distributed data. And in the case, if you don't know what sigma is, then you need this T distribution. Now the T distribution in a lot of ways is going to be familiar, but in some ways is going to be different as well. So one thing that's going to be the same is that its area, the area underneath the curve, the T curve is going to be 1. So let's see, do I want that one? No. Yeah, this one's a good one to start with. So here's your normal distribution, the top one. But one of the things you notice, even though the T distribution is symmetric around 0 with a total area of 1, is that there's this df here. That stands for degrees of freedom. So what does degrees of freedom mean? Well, let me illustrate it this way. Let me take a look at this row here. There's 4 people in this row. If I was choosing where to sit you, let's think about the number of choices I would actually have. I'd have my choice for who I want to put in the first seat. I'd have my choice for who I want to put in the second seat and the third seat. But after I've picked the first 3 of you, then there's no choice left for who gets stuck in the last seat. Because I've already picked those 3, that 4th seat is already preordained for somebody. So Kayla, we're not moving you. All right, you get to sit in the 4th seat. But even though I have 4 chairs, I really have 3 choices. So that's really kind of like your degrees of freedom. There's 1 less choice than the number that's in your sample size. And that's going to be typical for degrees of freedom calculations. The T distribution changes its shape depending on the degrees of freedom. So you might have seen me clicking around here. I had a different graphic for the T distribution. Here's another one. This one shows it a little bit better. So with 10 degrees of freedom, your T distribution looks like this. With 20, it looks like this. The larger your degrees of freedom gets, the closer it's going to look to an actual normal distribution. So the difference is kind of subtle, but it does make a difference, and we are going to account for it in our calculations. The good thing for us is that a lot of our technology will actually do all this stuff for us. But nonetheless, we're going to practice how to find a couple values from these distributions. So let's do that first. Let's go back to our distributions. We'll start with the graphing calculator first. Graphing calculator. command on your graphing calculator is inverse T, and it's going to be the area in the left tail comma degrees of freedom. In Google Sheets, it's going to be similar. It's going to be inverse T. Remember, in Google Sheets, you have to type in the equals first, inverse T, and then again, area in the left tail. And then again, degrees of freedom. I'm just going to write df there. The annoying thing for us is that's not exactly the notation that is in use in stat books. In stat books, you're going to be asked to find T alpha for particular degrees of freedom. Just like what it was in our Z distribution, alpha refers to the area in the right tail. So this is going to be alpha area in the right tail, and degrees of freedom for df. So there's a little bit of disconnect from our notation to the way technology works. That's all right. Let's see if we can't find a couple values. We'll start with T sub 0.05 for 12 degrees of freedom. Okay, now let's understand this. That means 5% of the area is going to be in the left tail. But that's not what I want to use with my technology. What number should I put into my graphing calculator? 0.95. So let's go to a familiar key, distributions. So second, and then the vars key. Inverse T should be your fourth selection down. Area of 0.95, 12 degrees of freedom. Should get about 1.782. On Google Sheets, the same thing happens. So equals inverse T. Inverse, oh, thanks. Was it T inverse? There we go, T inverse. All right, perfect. Inverse T. So area 0.95, comma 12. Yeah. All right, so, for some reason I thought it was the same. Thanks. You should be able to get 0.1782 from one medium or the other. Is that true? Are you guys able to get that one? Now, if you look back at our calculation for E, whoops, it's not, don't want that. If we look back at our calculation for E, a lot of times you need to calculate T sub alpha over 2. So let's just do one more practice with the T distribution, and that is T sub 0.05 over 2 and 26 degrees of freedom. Now it's up to you if you want to calculate that ahead of time or if you want to make your calculator just deal with it, whatever you want to do. But you do have to account for the fact that the area here is going to be the area in the right tail. Your calculator is going to give you something in the left tail. Charbel? Boy, statdisk, that's a good question. Let's play around with statdisk real quick and see what that can do for us. So we'll go to analysis, probability distributions, student t distribution. Degrees of freedom would be 26. And then, you know, depending on what you're looking for, you type in one of these blanks. Since we have the area, now this one asks us for the area to the right. So we're in good shape there. But the quick question is, what area do I want in the right tail? It's not 0.05, it's 0.025. So 0.025 gives me about 2.055, like that. If you're doing it on a graphing calculator or on Google Sheets, then I keep on clicking the wrong button here. This one. What should I type into my graphing calculator? What area? What value for the area? 0.975. Now, if you want to be really, really lazy, like I did here, you can take 1 minus alpha over 2, or 1 minus 0.05 over 2, and just let your calculator deal with it. All right, you just need that area in the right tail, so it's 1 minus that area is going to be the area in the left tail. So 2.055. Okay, are you comfortable with the t-distribution, finding values from the t-distribution? All right. The nice thing about technology is that it's going to be a lot easier to work with some of our problems here than it was for students in this course a generation ago. So let's take advantage of that. Let's embrace it. We'll start it with problem number 10. In the wrong section here. Just give me a second. So the birth weights of baby boys, summary statistics, birth weights of 195 boys, mean of 32.7 and a standard deviation of 6.6. We want to create a 95% confidence interval for these results. Basically, it's like, okay, well, what's the true population mean for the birth weight of boys? So we need to write down some relevant information. Let's do that. We've got 195 boys. X bar is 32.7. Standard deviation is 6.6. And we want to find a 95% confidence interval. So let me just replace that with this. These are our summary statistics. Okay. Let's start it out with the graphing calculator. On the graphing calculator, hit the vars key, or no, not the, let me think. Give me a second. Hit the stat key. Hit the stat key and then go over to test. We want number, at least on my calculator it's number 8. I think it's number 8 on the 83s as well. We want a t interval. We're going to input statistics. So not from data, but from statistics. So when you cursor over to statistics, press enter. It should give you a little menu, and you can just input all your statistics. So the mean was 32.7. Standard deviation was 6.6. And n was 195. Confidence level is 0.95. When you get all this entered, press the enter key and it should just do all the work for you. So it's going to find alpha, it's going to find the t value for the appropriate degrees of freedom. It's going to do x bar minus e and x bar plus e, and give you all that wrapped up into one nice, neat little confidence interval. So our confidence interval is 31.768 to 33.632. Okay, let's see if we can't state this conclusion in words. Before I do that, does anything seem funny about this result? Yes? Google Sheets would be a little bit of a pain. I wouldn't choose to do it in Google Sheets. I will go through and do it on statdisk. All right. So, tell you what. Before we do our conclusion in words, let's do it on statdisk. So statdisk, go to Analysis, then Confidence Intervals. What looks promising from this menu? Mean of one sample. 95% confidence interval. Sample size is 195. Sample mean was 32.7. Sample standard deviation was 6.6. Now here's something that I sort of alluded to but also left out earlier. When I talked about the error term, I said, well, if sigma is unknown, then we're going to use T sub alpha over 2 times S over the square root of n. That was our error term. That's assuming that the population standard deviation is not known. If it is known, instead of putting that value here, you'd put it here. But there's a reason that we don't use that. It's very unlikely that you would know the population standard deviation, but somehow not know the population mean. Typically, if you know one, you're going to know the other. It's not very often that you would know one without the other. So let's put it back here and click Evaluate. The nice thing here is that they actually give you the margin of error, which I like. Not that we couldn't get it from our graph and calculators output, but it's just a little bit nicer to have it here. So again, 31.678 to 33.632. Does that help? Okay, yes. Now, like I said, there's one thing that's strange about this. Does anyone know what's... Does that seem strange to somebody? This is the birth weight of baby boys. Does it seem like weird numbers for birth rate? Or birth weight? Yeah. I expect something between 6 and 8 pounds, typically. So, yeah. All right, but well, what's different? What's the solution to that is that they give the units in hectograms, which I've never seen people give something in hectograms. I wonder if he like converted that just to like throw people a curve. I mean, a hectogram? Okay, let's see. That's what, 100 grams is a hectogram, I think. Not sure. I'd have to look it up. And then 2.54 grams per ounce. I could convert it eventually, but hectograms is just a really, really obscure unit. I've never, ever seen anyone use it. So, kind of amusing. Whatever. But the point that we should get is the confidence interval, and then we need to state our conclusion in words that relate to the problem. We can be 95% confident that the true mean weight of boys at birth is between 31.768 and 33.632 hectograms. That's just funny that he uses that one. All right. Your conclusions should relate to words that describe the parameter relative to this particular problem. Shouldn't be completely generic, although you should start to see a little bit of a pattern in this. Let's try some more here. Problem number 16. Arsenic in rice. I think your author does a great job of doing a lot of these problems. Finding a lot of different data sets. So listed below are the amounts of arsenic in milligrams or micrograms per serving in samples of brown rice from California based on data from the Food and Drug Administration. We want to create a 90% confidence interval for this data. Okay. All right, so first thing first, we have to type in this data someplace, either into your graphing calculator or into statdisk. I wouldn't suggest Google Sheets for this. Let's start with our graphing calculator. We'll do this one with our graphing calculator, and then we'll do problem number 24 or 26, one of those with statdisk. To enter your data, type the stat key, and then press enter. Notice the first choice here is to edit your data. Now, if you have some data already in your calculator and you want to get rid of it, take the cursor all the way up to the top of column L1, press the enter button, and then press the clear key. It should clear out that entire column like that. So you should have a fresh column to work with. Now, to help you out, I'll read off the data. So you can just enter it into your calculator if you're following along, or you could actually enter it into statdisk if you wanted. If you're doing it at statdisk, just close this out and enter the data into a particular column. And then I'll go through in the next problem how we do that, how you'll evaluate it. But let's type in the values of 5.4, 5.6, 8.4, 7.3, 4.5, 7.5, 1.5, 5.5, 9.1, and 8.7. So that's where our data is. And I guess I should have clicked back over here. After you're done entering your data, you want to exit here. To do that, you hit the second button and then the quit key. Or second and then mode. Now we're going to create a statistical test. We want a confidence interval for this. So go back to stat, then over to test. And we want a t interval. So that's the 8th one down. This time, instead of entering in the statistics like we did before, we had the summary statistics, here they are for our last problem, we're going to enter it from data. So cursor over here to data and press enter. And notice what happens, it changes things. Now it's asking us to input things. It says, where's your data? Well, it's in list 1, L1, so we're good there. Frequency of 1, we can just leave that. We want a 95% no, we want a 90% confidence level, so 0.90, and then calculate. So there's your 95% confidence level. Can someone state that for me in words? What would this be in words that relate to the problem? Connor, want to give that one a shot? Arsenic levels. Perfect. and that's in units of micrograms. Perfect. So once again, we can be 90% confident that the true mean level of arsenic found in brown rice is between 5.0023 and 7.6977 micrograms. So hopefully that's not a lot, but it is what it is. Are we okay with the calculation? Charbel? Yeah, we're going to do a different problem with statdisk, but it'll still show you how to do it in statdisk. All right, I just don't want to take the time to enter the data here into statdisk. But it'll just be a one-click button. In fact, here, let me just show you how to do it. In statdisk, you would do analysis, and then confidence interval. This time you'd use data. So instead of typing in the summary statistics, you use data, and it'll ask you where your data is. So just click that column, you know, whatever it is. It should probably be in the first column, and then evaluate. So you should be able to get the same thing that we got. The nice thing about statdisk is that it can jumpstart some of our calculations. So the last one we're going to do then is going to be problem number 26. Bless you. It says refer to data set 32 for airport data speeds. Construct a 95% confidence interval for estimate of the mean speed for Sprint. Then do the same thing for T-Mobile and compare the results. Okay, so this one, like I said, we'll do with statdisk. So I'll shut this off. The nice thing about statdisk is it comes with some built-in data sets. So click data sets. Then go down to Elementary Statistics, 13th edition. You want data set 32, airport data speeds. So you click this and a whole bunch of data should populate your screen. Nice. If we want a 95% confidence interval for our data here, let's go to Analysis, Confidence Intervals, Mean One Sample. And again, click Use Data, because that's what we want. We want to use our data. And let's see, we wanted Sprint. So Sprint is in column 3. I have no idea what units this is in. So I trust it's in like megabits per second. Yeah. So we can be 95% confident that the true mean data speed for Sprint is between 2.1 and 5.3 megabits per second. Let me write those numbers down, and then we're going to do a little bit of an experiment here. We're going to kind of veer away from what the book is asking us to do, and I want you to think what would happen if I repeated this confidence interval, not for a 95% confidence interval, but for a 99% confidence interval. What do you think is going to happen? Are you going to get the same thing? Is it going to get bigger, smaller, larger? Seems like you can guess, but we'll find out. So for problem number 26, we had a confidence level of 2.11 to 5.03 or 30. No. Yeah, 5.30. So 95% confidence interval. Let's take a look at that same thing for a 99% confidence interval. So I'll just retype that. Evaluate. This time I get 1.58. I'll call it 1.59 to 5.83. All right, let's switch over to this screen here. Where is it? There we go. So take a look at your 95% confidence interval and your 99% confidence interval. This is for problem number 26. How do they compare? Ryan, any conclusions? What's the difference between those two confidence intervals? In general terms, not number terms. Angela? Yeah, it got wider. Why do you suppose it got wider? You want to be more confident, right? If you want to be more confident, you give yourself more room for error. And that's exactly what's going on here. So the wider your confidence, or the higher your confidence level, the wider that interval is going to be. Now, what could make that shrink a little bit is if you had a larger sample. That would help your confidence interval shrink a little. But that may not be something you can control. So you might be stuck with a wider confidence interval. Depends on the consequences. Depends on what you're trying to estimate. How important it is that you be right. What's the consequences of being wrong? Okay. How are we looking on estimating a population proportion or population mean here? Shabo? Yeah, the higher the level of confidence, the wider your interval is going to be. Always. Not only with population means, but population proportions, standard deviations, all the different parameters that we estimate. The higher your confidence level, the wider that interval is going to be. Always. Okay. For homework in section 7.2, try problems 9 through 27. 9 through 27. We might add to that next time. Have a good one. See ya.